Hi guys, welcome back to Data Every Day. Today we're looking at a data set of credit card clients, and we're going to try to predict whether a given client will default or not. So it says this data set contains information on default payments, demographic factors, credit data, history of payment, and bill statements of credit clients in Taiwan from April 2005 to September 2005. You have a number of variables, and I guess we should just hop into the notebook and take a look. So I'm going to import NumPy and Pandas just for working with the data, and a standard scalar and train test split function from sklearn for pre-processing. And I'm just going to train 3 different models on the dataset: a logistic regression classifier, a support vector machine classifier, and a multi-layer perceptron classifier, or neural network. Let's go ahead and import those, and then I'm going to load in the data using pandas.readcsv. I can get the file path right over here, paste it in, and take a look. And so I have 25 columns, which exceeds Pandas' default limit for how many columns to display at once. So we have this ... here. I'm just going to head into the console and type pandas.setOption, setting max columns to none. This way we can reload it, and you'll see we can now see all 25 columns at once. So we have this at the end, which is default payment next month, which is a flag that indicates whether the client will default on their next month's payment. So we have a 1 if they do default, and a 0 otherwise. And we have a number of other features. Now, what's good about this data set, it's very clean. We only have to worry about scaling the data and maybe encoding a little, but there's no text data. It's all numerical, so it makes our life easier. So what I'm going to do, well, first let's get a little information, data.info. This will tell us if we have any missing values, and it looks like we have no missing values. There's 30,000 total entries, and in every single column we have 30,000 non-null values. Additionally, we can see there are no object columns, so let's get on into pre-processing. And I'm just going to create a function called preprocessInputs that's going to take in a data frame. In this case, we'll pass in data. It's going to start by creating a copy so that we can retain the original version, then just modify a copy of it. And we're going to return x and y, where y is going to be the column of the data frame which we're trying to predict. In this case, it's default payment next month. So I'll say y equals df sub default payment next month, and I'll make a copy of that. And then x is going to be everything except that column. So I'm going to drop it from axis 1 and make a copy of that as well. This will return both x and y. So just comment this, split df into x and y. And now x comma y equals preprocess inputs, and I'm passing in data here. Now you can see x and y have been split. So y is what we're trying to predict, and x is everything we're using to predict it. And now we can just add any sort of transformations we want in here, any sort of pre-processing transformations, and we can keep checking the results of the function. So let's take a look at what we need to do to this to get it ready. Well, I noticed the ID. ID is not actually giving us any useful information, right? So I'm going to drop ID, because ID is going to be unique for each one, and in fact it's just another index column, so we don't need it. df equals df.drop ID axis 1. Now we can run it again, and you'll see the ID column is now missing from x. So I'd like to actually visualize the correlations of this data set really quickly. Visualization. Let's just do it on the original data. And I'm going to, in here, I'm going to import matplotlib.pyplot as plt and seaborn as SNS. So we're going to use Seaborn and matplotlib to generate a heat map of the correlations so we can understand which columns are affecting each other. So we'll start by creating a new matplotlib figure. Specify the fig size. 12 by 10 works well for a correlation heat map. And we're going to plot the heat map with sns.heatmap, passing in we have to pass in the correlation matrix, so let's calculate that. Easy to do that, just data.core. And we'll store it in core. So we're now going to plot a heat map of core, turning on annotations, setting the minimum value, and let's give it a nice color. The Mako color map is quite nice. And I believe that's all we need. Plot.show. Well, we can give it a title as well. Let's make it a little bigger. I can't see so much. So let's make this 18, this 15. And then I'll just give it a title as well. plt.title correlation heat map. Alright, now we can see it. So we have to remember we're going to ignore the ID column here. It's not really telling us much. We can see we have quite a few positive correlations around this area. So that's the bill amounts 1 through 6 are very positively correlated with each other. And that makes sense because I think a given client will probably have a similar bill amount. And as one goes up, the others will as well. And then these pay 0 through pay 6 columns, I believe this is it's how their repayment status. So it's -1 if they pay duly, 1 if the payment is delayed for 1 month, 2 is payment if they're delayed for 2 months. So this is an ordinal variable that measures how late they are in their payments. And it makes sense that if they're late on one, they're probably late on others, and vice versa. So you can see we have some positive correlations here, some positive correlations here, and other than that, we really don't have many correlations at all, except maybe this one. The age and marriage is negatively correlated. That's interesting. So let's take a look at what's marriage. If we look at, oh, actually, I think marriage is a nominal feature. We look over here, marriage. Marital status, it's 1 for married, 2 for single, 3 for others. So you can't really observe correlations with a nominal feature because there's no ordering between these. A high value of marriage doesn't mean anything. So we can ignore that little black spot. Everything else seems pretty uncorrelated. Additionally, this one I'm interested in here. This is the column we're trying to predict. Also this row at the bottom. You can see we have no real strong correlations with what we're trying to predict. Which means if we get a good performance of our model, it's not going to be because of a single column or a few columns, but rather as a result of a combination of all of them. Alright, so let's now get back to pre-processing. And right now we have, pretty much all we have to do now is deal with these ordinal, no, the ordinals are fine. We have to deal with the nominal features, which is education and marriage. If we take a look at, here, why don't we get a dictionary? It's going to map a column name to the length of unique values in the columns. Not df, it should be x. So x subcolumn dot unique. This will just give us the unique values in a given column, and we're going to take the length of it and display a mapping between the column name and the number of unique values for every column in x.columns. So we can see this limit balance. This is actually a numerical feature, so we don't have to be concerned with that. Sex is a binary feature, so it doesn't need to be encoded any further. This still means, even though we're not here saying that one sex is greater than the other, we're saying that there's like two directions, that either the model is going to notice either it's to one side or the other side. So a binary feature, as long as it has two unique values, it doesn't really matter how far apart they are, what the values are, because especially after we scale it down, it's just going to be sort of like a switch that the model understands, either 1 or 2, back and forth in a different direction. Education and marriage. These ones, 7 and 4 values respectively, they are nominal features, right? And you can tell that over here, it tells you what they are. It's possible that we could call this an ordinal feature because there's some sort of progression between the schooling categories, but because we have these unknowns at the end, it would be very difficult. We also have others, right? It would be very difficult to order them. Same here, we can't really order the marital status. However, age and all of these are already ordered. actually the pay amounts here and the bill amounts are actually not even categorical at all. They're just numerical columns. And then these here, pay 0 through pay 6, are ordinal columns that display, again, how late someone is on their payment. And it's already ordered for us, so we don't have to worry about encoding them. So it looks like the only thing we really have to deal with are these two columns here, education and marriage. And they are nominal features. The reason I'm encoding them is because we don't want the model to think that, for example, 3 is higher than 2. It doesn't make sense. I mean, yeah, look, 3 is high school, 2 is university. So we're saying that high school is higher than university and others is higher than high school, which, I mean, this isn't really an ordering here, right? So we want to make sure each unique value has its own column and its own feature. And for that, we are going to use one-hot encoding. So let's go ahead and create a one-hot encode function that takes in a data frame, and I'm going to pass in a column dictionary, column dict. We'll start by creating a copy of our data frame, and at the end, we're going to return our data frame. But in between, what I'm going to do is iterate through column dict. This dictionary is going to have pairings between a column name and a prefix for the one-hot columns. So let me show you. We can use pandas.getDummies to, let's use the education column. We pass in a column and get the dummies for it. What that'll do is it'll take, it's a little hard to see, but all this 0 through 6 here, these are all the unique values of education, right? So in education, we have values that take on 0 through 6. Now each of those unique values has its own column, and we have a 1 or a 0 depending on the value for a given example. So for example, you can see all these first 5 examples have 1s in the 2 column. That's because if we go down here, there's 2 in every single of the first 5. Down here we have 3, 3, 2, 3, 2. So if we look back here, we're in the 3 column, 3 column, 2 column, 3 column, 2 column. So that's how dummies works, and we can also include a prefix here. How about edu for education? All that will do is put a little prefix at the beginning of each column so that we know where these original column names are coming from. Alright, so what I'm going to do is I'm going to create a dictionary that's going to map a column name to a prefix. And we're going to pass it in and sort of take it apart inside the function. So what we'll do is note, let's say, okay, let's actually create it. Education is our column name, and it's going to be mapped to edu as a prefix. Here's the dictionary. If we call it .items on a dictionary, it will allow us to iterate through as tuples, pairing key values as tuples. And with a tuple, we can go in and say for column comma prefix in column dict .items. So you see, this will give us the tuples, and then we can iterate through tuple by tuple, extracting the values from it as we go. So we can get column and prefix at the same time. And we're going to create a dummies data frame using pandas.getDummies, passing in df sub column. So this is for a given column, and then a given prefix. So they go together, column prefix from our column dict. Then we're going to concatenate together the original data frame and the new dummies side by side. And then when we're done, we're going to drop the original column from which we created the data frame. And that's it. This is our whole one-hot encode function. And down here, after we drop the ID, but before we split, all we have to do is say df equals one-hot encode, passing in df, and then we're going to pass in our column dict, which is going to map column name to a prefix. So as I said, we're just doing these two. So we have education that gets mapped to edu as a prefix, and we have marriage that we can map it to mar. Why not? So here are our prefixes, here are our column names, and if we run this, you can see our original columns are gone for marriage and education, and now at the end we have these edu columns that were generated from the education column, and these marriage columns that were generated from the marriage column. And now you can see each unique value has its own column, so they're not going to be confused. The model won't consider them as ordinal features. Okay, so we're done encoding. That's all we needed to do for this one. Last thing to do is scale. So scaling will give, it will make sure that each column in X takes on a very similar range of values. So right now we're on totally different ranges. This one here you can see goes from -1 to like 6 or something, or I think it's to 9. But so -1 to 9, and up here we have something like 19,000, 20,000, 30,000. So it's very different scales, and we want to squish all the rows, standardize the rows, columns, so that each column has a mean of 0 and a variance of 1, and that will ensure that most of the values in each column lie between -1 and 1. So we're going to do that with a standard scaler. So we're going to scale X with a standard scaler, and you'll note at the top I imported standard scaler from sklearn. So let's go ahead and use it. I'm going to create a new scalar object, and then we're going to scale X using scalar.fitTransform. I'm passing an X here. This will just apply the transformation so that each column has a mean 0 and unit variance. And then we can, here, this actually returns a NumPy array, and I want to keep it as a data frame. So I'm going to turn it back into a data frame once that transformation has been applied. And I'm going to keep the column names the same as they were before. Alright, now we run this, and we check right now. Before I check it, you can see all the columns take on different ranges of values. Afterwards, you can see they all take on the same range of values. If we look at the means of X, every mean is very close to 0, extremely close to 0. And the variance will be, you can see, is about, it has 1 variance, very close to 1. So now our model will consider, standardizing solves a lot of issues with the model and definitely increases the performance. Alright, so now let's actually train the models. So like I said, I'm going to train 3 different models. It's going to be a logistic regression model, support vector classifier, and MLP classifier. So let's create models. I'll make a list of them, and I'm just going to actually create new instances inside the list. So that's an instance of logistic regression. Then we have SVC, or support vector classifier, and then how about we do this? I'll make it a dictionary instead of a list, and then I'm going to map each object to a name, a model name. Logistic regression, and this gets mapped to support vector machine. And then last we have the MLP classifier, which is a neural network. Okay. And let me just change these to no good. I prefer double quotes for this kind of thing. So just give me 1 second. Okay. That should do it. I'm just going to straighten them out a little. I'm going to give them equal spacing so we can see. And I actually want to make sure that they're straightened on the edge so that I can display the results like right here. Alright, we have our models, which is a dictionary that maps a instance of the model to the name. And then we can say for model in models, so each model is going to be, actually for model in models.keys, right? This will just go through the keys. Model dot fit xtrain ytrain. So we're going to fit the model on the train set, and I realize I haven't actually created the train set yet. For that, we're going to use the train test split function from sklearn, which will pass in x and y to, and specify a train size of 70%, and we'll include a random state. This function also shuffles the data, so I'm going to include a random state so we can reproduce the shuffle and split each time. And then this is going to be stored in xtrain, xtest, ytrain, and ytest. So it's going to split x and y into train and test set. Then we're going to train the model on the train set. And x. Oh, I didn't run this. Okay. And now all three models should be fit after that is done. And then we're going to print the results as so. So actually, for model in, well, say we're going to iterate through two at a time. Model and name in models.items. So items, again, this gets the tuples, this to this, this to this, and so on. So we're going to print out the name plus colon, space, and then let's score the model and store it in here. So I'm going to display it to, how about 4 decimal places, and dot format, model dot score, scoring on the test set. I think this is good, right? Okay, that took a while, but I think this should do what we want. Oh, actually, let's show it in percentage form. So percent here, and then I'm going to multiply this by 100. Oh, this should not be a plus. This should not be a colon, it should be a plus. Okay, so it's we got an 81.4% accuracy on the logistic regression, and we got worse performances on support vector machine and neural network. So that's interesting. I think I want to display this to 2 decimal places. But it looks like a simpler model worked better in this data set. Logistic regression. Oh, here the SVC actually pulled through and has more. But they're more or less around the same, 80 to 82%. And that will sum up today's video. I just want this to be a very quick sort of tutorial on how to get a data set working with machine learning. Thank you so much for watching. I hope you enjoyed the video. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.